So my presentation today on standards updates. I have a few bullet points on topics that I will address during this presentation. Standardization priorities is one of the issues. What are our priorities currently in the standardization working group? Progress with new extensions. Support of DR environment, another topic that is quite hot in the context of 61850 as well. Verifying STL, an area that we started, and we will see a couple of things related to that. And at the end as well, a little bit about the roadmap of 61850. So let's start with standardization priorities. One of the higher priority in our various work, those of you that are a little bit familiar with the 61850 work, we have typically multiple parallel ongoing activities in the working group dealing with different topics from communication aspects to data modeling aspects like engineering or security. One of our key areas where we have a couple of activities is still around specification and engineering process that still has one of the higher priorities. Those of you that were yesterday in the pre-conference workshop have heard a little bit what we are doing with regard to specification, what is the visions of utilities, how they want to move formal specification based on 61850 to the next level. And the work around this topic is one of the priorities in our standardization work. This also includes some work related to system management meaning the way how you can manage your devices out in the field, maybe from remote. If you have many devices distributed in your networks, that may be a useful possibility. The target is still integration shall become easier. As you know, you have many utilities have a number of substations that they have to maintain. The number is sometimes quite significant, and with the limited workforce in order to maintain, refurbish all these substations, we need to have more efficient processes. Reuse in that context is one of the key elements that we can reuse concepts, reuse library elements in our designs and deploy them to have a better productivity in creating new substations. Of course, that applies if you as a utility have standardized environment that you can apply the same functions in different substations. Integration of physical resource in the design process is one of the topics as well that we are considering currently. Specification and engineering process. As I mentioned, those of you that have been in the workshop yesterday already heard about some of that. So one of the work related to that is a new technical report called IEC 61850-90-30. It's about, the official title is about guidelines for IEC 61850 function modeling in STL. In this technical report, we define a couple of extensions to the system configuration language, the STL, for the enhancements of the specification and engineering process. The namespace for that is called 6-100, which was the first number that we used, but we had some reasons to change the number of the report itself. But the namespace identification will still be 6-100, and that will include in the future as well other extensions. So what are the key topics that we address in that technical report? One aspect is the modeling of functions and application schemes. The other one is about data flow in the functional part of STL, which allows us to define detailed scheme implementations independent of ID implementation. We will talk a little bit about that. And then it's also the introduction of virtual IDs and the ID specification file. So what are these topics about? First, functions and application schemes. One element that we introduce is a function-subfunction hierarchy that can be added to the substation structure of system configuration language, where we define the single line diagram, the topology of the substation, where we define the requirements in terms of logical nodes or L nodes. We now can add those. Okay, the pointer doesn't really work on the screen. We now can add those in a function hierarchy. So I will point here more or less. So what we see here is we can create a function, sub-function hierarchy where we have logical nodes now associated to sub-functions. These sub-functions can get textual descriptions like in the example here that you probably cannot read from the back. The function is a distance protection. We have a first sub-function which would be the switch on to fold backward function. The other one would be the switch on to fold forward. Then we have a sub-function for the zone 1, the zone 2 and 3, and so on. So we can label these sub-functions, we can give them textual description, and with that we achieve basically one of the goals that was a lack in the past when you have multiple logical nodes of the same common data, of the same logical node class, like multiple PDIs, multiple PTOCs. It was hard to know which one is doing what. With that, we can really, by giving them these function, sub-function names, we can identify them, what they are doing, what role they are playing. And there's also discussions that we may standardize in the future sub-function and function types to even achieve a higher interoperability. But that's still an open topic. The other element we introduce is the application schemes. With the functions, sub-function hierarchy, we can put functions in a hierarchical context, but a function may participate in multiple applications. As an example, the breaker function that we have on the right side here, the function that is interfacing the breaker, this function participates in this example in the breaker failure function application, but this function also participates maybe in the tripping in the protection application for tripping. It participates in a control function that is doing a controlled operate of a breaker. So by introducing this concept of applications where we more or less refer the different functions that work together and where we can also define the information exchange associated to this application, we can have a better level of documenting our requirements or documenting our implementation. So that's another element that has been added or will be added with this 90-30. In order to document the interaction between the functions for the application, today we have the xref, which is basically between logical nodes that are already allocated to IEDs. But if we want to do such a specification already at specification time, independent of IEDs, we needed an additional element, and that's why we also introduced, or will introduce, what we call the source ref, which is a similar element like the xref, but it's not between the logical nodes within an IED, it's now really between the logical nodes from a specification perspective. So that's a third key element that we introduce in this 90-30. And that really allows us to do already at specification time, specify detailed schemes with the required information exchange, and this independent of a device allocation. If you want to define function allocation for devices in specification, we are introducing the concept of virtual IEDs. So we now have as well the possibilities in a specification to add IEDs. These IEDs are not real devices, that are IEDs from a specification perspective that group the functions that you as a user want to have implemented in one device. So basically we allocate functions to virtual IEDs. You may have virtual IEDs like a merging unit, a bake control unit, a protection unit, or a switch control unit, and we can define with the specification what functions and as a consequence what logical nodes shall be allocated to these virtual IEDs. And then we also can create out of that what we call an ISD, which is a new variant of STL files, which is an IED specification description file. And this can then be used more or less as a specification towards an IED vendor. And the ID vendor, based on that, can return the ICD file that fulfills these requirements. And with that, you also have a way to verify machine-based if what is proposed by the supplier corresponds to what you expect from a utility as a requirement, or from a user perspective as a requirement. So that's some of the new elements that will be added in this technical report 90-30. They have been tested already in some pilot projects. As an example, we had a European research project called Osmos, where we evaluated this process. Some utilities have started pilot projects to verify these concepts and to make sure that the vendors start supporting that and start to implement that in the products. What else is going on? I mentioned system management. System management will be a new technical specification called IEC 61850-80-7. It will deal with communication services and data models to support system management. It's basically implementing work that has been documented a while ago in the technical report 61850-90-16, where we have collected the requirements for system management. So now with that work, we are getting into the next stage where we are implementing those requirements, defining what is needed, what needs to be extended in the standard, what needs to be defined in order to support that system management. The key application there is really for remote management of your multiple IEDs, and it was driven more or less by utilities that plan to use 61850 in all their distribution substations, so that you can imagine if that's a larger utility, there's many distribution substations where you have this equipment, when you have to do configuration upgrades or when you have to do software, firmware updates on the IEDs. You definitely don't want to travel to all of these places and do it locally. You definitely need some mechanisms to support the management of your IEDs from remote. And that's a little bit the context of that work. The good thing, both this activity as well as the previous activity on specification are really supported by utilities. The whole specification process ELIA is pretty active in supporting that. System management is supported by EDF, driven by EDF, so it's not just something that is invented by vendors that want to try to sell new stuff, it's really something that is supported and required by the utilities. So we are really to try to be utility user-driven on what we are adding to our standard. And I think it's very fortunate that we have utilities that are active and looking into that and moving the world forward. Okay, we talked as well about reuse. When you have your standardized substations that have more or less same concept in different substations, you want to be able to deploy configurations based on your standard templates. And one work that is going in this direction is what we call the basic application profiles. Basic application profiles have been introduced as concept in a first edition of the draft 61850-7-6, which was called Guideline for Basic Application Profiles. And the concept of BAP was there introduced, and it was also a template was provided how you can describe a BAP with more or less a textual document. What we are working on now is to bring that concept of basic application profiles to the next level by adding a formal way to specify a basic application profile using the system configuration language, so that later on, when you build your application, you can use that as a starting point, as a template of your applications, and then you can automatically apply that, instantiate the required functions into your system design based on your single line of the substation. As an example, what we are doing there more or less, we are describing the applications with the different functions that we need and their roles. Like when you look at a breaker failure application, you will have a function that is the breaker failure detection itself, that has the role of that. You have a function that is the breaker interface of the local breaker, and you may have a function that can be instantiated multiple times, which is the breaker interface of the remote breakers that have to be tripped in case of a breaker failure. And all that is described using STL, including the roles of the functions and the multiplicity, if a certain function is there multiple times, and on what kind of feeders that has to apply. And once you have this described with the data exchange, you can, when you build your substation, tools can automatically instantiate that, create the required functions, create the required data models, and create the required signal flow. So that's really one of the key elements to improve the efficiency in deploying IEC 61850-based substations. Again, this is adding extensions to STL. It's based on the 90-30 technical report where we introduced the concept of application, but it's adding a couple of elements, and it's one of the key elements when we want to do a detailed top-down specification supported by STL. Physical resource management is a next topic. That's in a technical report 90-29. Basically, what we are defining here is extensions to describe aspects of the physical resource of a system. It includes model extensions to model physical inputs and outputs of IEDs, a requirement that has been long raised in the past already by some individuals. And finally, we are adding that to the standard there. It's also ongoing work, but it will also have quite significant value. If you look a little bit at the planning of these extensions, so the most advanced is the work on the 90-30. We had already first 2 drafts. At the bottom in green, you see what this abbreviation means. We already had 2 drafts circulated. We are now working on the draft technical report, which is basically the final stage before publication. The 7-6 has started a little bit later. We expect to have a first CD somewhere next month, and somehow next year we hope that we can publish the draft technical report of that part. 90-29, we had a first document circulated last year. We are working on a second document. There's still a lot of work to do. We are entering some new areas there. That's why it takes a little bit more time. Plan is that somewhere in September next year we should have a second draft, and somewhere in 24 that should as well be completed. And the system management, we are planning a first CD for the December this year. That's correct. We have the task force leader here, Thierry. And the draft technical specification should be in December next year. So here, as I mentioned, that's based on a technical report we had where we have defined all the requirements. That's why we have already a lot of work done. The implementation shouldn't take that long. So you see these elements are more or less coming, finalized somewhere in the next 2 years, then they should be available. But based on pilot projects and evaluation projects, when they are already starting to implement them, so once the standards are there, I think also products should be close to be ready to support that. Okay, talking about progress, another area where we are doing some progress currently is the communication to control center. Some of you may still remember there was a technical report, 90-2, published a long time ago, that was dealing with the aspects of using 61850 to communicate from your substation to control centers as well. So to replace existing SCADA protocols like 871.5.101, 104 or DMP3, using 61850 really from the bottom up to the control center. Recently that work has been reactivated, and we are now working on a technical specification, which is a little bit a more important document than a technical report only. And the topics that we discussed there more or less is the communication from a proxy or gateway in your substation to the control center. We are addressing the communication aspects of such a link, redundancy schemes, which are very important in that context. Sometimes you have redundant controls, front ends in the control centers. You may have different control centers. You have redundant gateways. How are these different redundant levels working together? That's some of the areas discussed there. engineering process as such for the proxy or the gateway in the context of 61850. Functionality, what functionality does the proxy or the gateway have by themselves? Typically you are maybe buffering, you have a local database and the event communication to the SCADA system may not be exactly driven by the reporting within the substation. So that may be decoupled. Data modeling aspects are discussed and service mapping is discussed. So how does a control service that you do between the control center and the gateway, how is that mapped on the control service from the gateway down to the IED? So these are the topics addressed there. As I said, the work has been reactivated by bringing that now to a technical specification. Okay. DR environment. DR environment, I think I already told about that during the last 61850 virtual conference. For DRs, the international standard 61850-7420 exists for a while as a first edition. This has been completely reworked, and the second edition has been published more or less last year. And what we see here is the basic elements that we are now modeling. So the whole standard has been looked into the aspects mainly of generation from a more systematic way. We have tried to decompose how a typical functionality of a DR system works and create relevant logical nodes. So basically, what we have in this standard is 4 major groups of logical nodes. On the right there you see the DR resource. DR resource is the DR itself, and there we have 2 categories of logical nodes. The first category, which is the specific ones, so we have logical nodes modeling photovoltaic installations, logical nodes modeling the specific aspects of a battery or of a diesel generator or whatever you can imagine that you have as a DR. But then I think the important concept that we came up is from a integrating perspective, from a utility perspective, you are not really caring too much about the technical details of a photovoltaic versus a diesel generator. When you look at it from a network perspective, a DR is typically a generator, or it's a load, or it's a storage system. So we introduced as well in the DR resource concept some generic loads that model the generic capabilities of a DR as a storage device, as a generator, or as a controllable load. And that's really where the system interacts. And to interact with those nodes, we typically use a power management function, which is taking into consideration various requests. We may get requests to a DR from a utility perspective to produce something, to do certain functionality. But as a DR, we also have to fulfill grid codes. We have, as an example, to fulfill write-through capabilities. And that's what we are all modeling in what we call the operational functions. So typically a DR will have multiple operational functions that try to influence what the DR is actually producing or consuming. And it's the power management function in between that is implementing that. And last but not least, an additional group of logical nodes that we define there is the electrical reference point. That's more or less the point where the DR is connected. It can be a point of common coupling to utility network, but it can also be just a local reference point in a larger microgrid system as an example, or it could be also a virtual reference point in some cases. You may refer to some virtual measurements to perform certain DR functionalities. Now, how does this translate in the real world? And again, in the OSMOS project that I mentioned before, which was a European research project, a piece of our work was as well to look into how this standard can be applied. And as the project was dealing with storage systems from a generic perspective, in our little subtask, we were looking as well as an application for a little storage system, basically. It was a battery system, and it was only done with simulation and with software simulation, basically. But we imagined the use case of a battery system that you have on the 2 ends of a power line, and the battery system has the goal to to maintain the load over the line to a maximum. That means when the load would have been exceeded, the rating of the line, at the source of the energy flow, the battery would consume the excess energy, and at the sink of the energy flow, the battery would feed into the system, the other battery would feed into the system the same amount of energy to keep the balance stable, independent of this shortage. So basically it's a virtual power flow implemented. And with that, we more or less demonstrated how we would use the different logical nodes. So on the left side here, we have the logical nodes for the different operational functions that we needed. As an example, there is an operational function defined for load following. That was mainly the operational function that determined how much load needs to be consumed. So the function has a certain threshold, and the load is going above that threshold. The output of the function is more or less the different energy, and we use that to load the battery in that case. We had other functions like active power control, DWGC. That was more or less the request to the other side of the system to produce the same amount like has been consumed at the source. So basically there was a bunch of operational functions, and then the power management functions got all these requests and has finally determined the output to the battery. Did it need to charge a certain amount? Did it need to discharge a certain amount? And has also sent the information to the other side. So that's just a little application. As I said, it was simulated using software tools to validate the concept, and the main purpose was really to validate the data model. And I think as part of that, we could prove that the concept as such, as the logical nodes are defined in 7-420 works. We can really build applications using that. But we also identified that as 7-420 has a large collection of comprehensive data, some of the data there is redundant. The models that have been defined there use sometimes different ways to model more or less the same information. As an example, set points, you have the options to use them either as a percentage or as absolute values. There's a couple of optionality in there, and there's a lot of data in there that you may need in certain cases, but you don't necessarily need them in all the cases. So one of the lessons we learned out of that exercise is that in order to really achieve interoperability with DRs based on that standard, we need to do certain profiling for specific applications. And some profiling work for 7-420 has already been started. It's mainly driven by the NIST, National Institute for Standardization from the US. We did some work already 2 or 3 years ago where we created the first profile based on the 7-420 to model all the grid codes that are defined in the IEEE 1547 standard. For those of you that are familiar, it's a standard that defines data points, information requirements for the various grid codes like voltage right through, frequency right through, volt-var, and all bunch of grid codes that exist are defined, the data requirements that you have to support as a DR. And the first profile we did a few years ago, where we more or less modeled all that using the 657-420. So we basically could show that we have all the information there, but again, it really needs a profile because you have to select from the large set of data what is needed. And currently there is work ongoing again under the coordination of NIST together with the Smart Electric Power Alliance, where we develop a DR interoperability profile not only for the grid codes, but as well for some generic applications. As an example, we look at DRs that have support functions like active reactive power control, frequency control, voltage control. So we are collecting the requirements for these use cases. We are mapping that into the 657-420 model and trying to build, based on that, a profile that can be used out of 7-420 for those applications. This is ongoing work. outside of the standard, basically, supported, as I said, by NIST. Verification of STL files, that's another topic. Basically, what you can do with standard STL tools, you can do a syntactic validation of an STL file against the XML standard. It's pretty easy to verify that you have your opening tags, your closing tags, that fit. That can be done by software tools today. We can also do a semantic validation of an STL file against the schema, but the schema alone cannot describe all the constraints. So basically, with XML tools, standard XML tools using just the XML schema that we have defined in the Part 6, we cannot really validate additional constraints on the values. As an example, those of you that are familiar with the details of STL, many elements or attributes are references to some other elements in the model, and the rule that this element needs to be there somewhere cannot really be defined with an XML schema. So that cannot be, by default, automatically verified. And during the IOP, the interoperability testings that we do every few years in 2019, we figured out that there were a lot of issues with the quality of ICD files. And then when your ICD files are bad, the system file gets bad. So we had a lot of challenges doing the integration of the application that we typically build at an IOP. That's why we came up with the need to have a better way to verify STL files. And the solution that we are now working on, and there is a new technical specification that will be started, and it will be called 6150 Part 6-3. And the title of that is Format of Machine Processable Rules for Validation of 6150 XML-based files. So the goal behind that is basically using OCL, Object Constraint Language, which is a language defined by the web industry, so it's not something we invented for the 6150 world, but it's a language that allows to specify machine processable constraints based on a UML model. And the idea is basically, with this technical specification, to provide the framework how to do these validations and then have all the rules that apply in addition to the schema, as an example for STL, rules like that this field needs to be an address that is pointing to a data set, to specify these rules that are today written in text, to specify them using OCL. A basis for that is the first thing we needed is a UML model of the Part 6. So we developed that UML model of the Part 6, and based on that, we can now generate those rules, and using then code to apply these rules, we will be able to validate the files based on the level beyond what is done by a schema validation. So the work is ongoing there. The rules there is not only rules coming from the Part 6, there are rules that come from Part 7.2 that defines how a report control block looks, how the different values need to be filled in. And the idea is really that these rules will be published for each of the parts of the standard that has constraints. There will be in the future a code component that describes all these OCL rules, and then validation tool, verification tool that apply these rules based on the 7-6 guideline can really evaluate that, and with that we should be able to have a better way to validate STL files and to achieve the quality in the STL files that is needed. As a proof of concept, there has, again, that's an initiative coming from a utility, in this case again EDF. As a proof of concept, EDF had developed some first set of rules and as well an environment called Rice Clips. That's a tool that can apply these rules and verify based on the rules an STL file. So that has been developed over the past few years. And for the IOP 2022, as I mentioned before, in 2019, we had experience with bad quality of ICD files that then migrated as well into the SCD files. And for the IB 22, that happened this summer, which was a physical IOP as well, For that, a team from EDF Hydro-Quebec and Triangle Microworks applied this concept, validated all the ICD files before they got into the system design, sent back the feedback to the vendors they had to fix their ICD files. And I think with that we could really show that the concept helps, works, and really helps to improve the design process of STL. So talking about the IOP, those of you that have been at IOPs, what we do since a couple of years there, we try not just exchange data, but we try to embed all the devices of participants in an integrated application where we model more or less a substation automation system. It's just a multi-vendor system because more or less every relay is from a different vendor. We integrate that in an integrated application. And I think this year we managed for the first time to have the system more or less configured and running pretty early in the week and do a couple of functional tests of the different devices of the system as such. Last IOP in 2019, we just managed to have it more or less configured the last day, and we could run one short test. But this year we really, and I think it was due to the progress, of course, in the products as such, but also thanks to the validation of these STL files, that we had better quality files that really allowed us for a faster integration and do some successful functional testing at the end of the week. Okay, last item, roadmap. This is the high-level roadmap of our activities, summarizing some of the key activities that we are doing. So basically, this year, main targets are related to user experience, enhanced specification capabilities, including ID specifications, so the 90-30 report should be somehow finalized this year or early next year. Redundant devices is an open work that still needs to be finished. Model extensions, we are working on travel wave-based fault location. We should get to an end of that. Technical report should be published. Communication-wise, we have a work on network diagnostics and auto configuration that should as well be finished more or less this year. For next year, some additional thing, I mean, some of them we have seen, additional topics that we didn't mention yet is the alarm handling. We are already working for a while on a standardized concept on alarm handling, how do we acknowledge the alarms and so on. That should be finished next year. Role-based access, so security-related stuff. Mapping to Modbus, mainly for the monitoring direction we are currently working on. The idea here is really to be able to describe a Modbus device in the context of a 61850 data model using the system configuration language where we can map then data points in a Modbus register to certain semantic objects in 61850. We are also working on a technical report validation of goose and sampled value message. And on the right side, that's a little bit the longer work. Refactoring UML model, starting with edition 3 of the core parts. HMI configuration, so some areas where user configurations will be improved. System management that we mentioned before, physical resource management. Additional model extensions, like probably revision of the power quality models that we have already, models for condition monitoring, and then also communication to control centers. That should be more or less be ready a little bit further. As I mentioned, we started to plan the edition 3. I'm looking at the time down here. We still have some time, I think, yeah. We started to plan edition 3. We have a planned amendment for part 7.3 that we once had planned. We cancelled that one. The idea was to support some requirements from 7.4.20. We proposed an amendment that would have integrated some concepts needed by 7.4.20, but we identified the complexity of the topic required more discussions, and as the reason we wanted to do an amendment was to get more or less in short time something that conflicted with the need for more discussions, so we decided to cancel that amendment and to integrate that in the edition 3. First priority in edition 3 is this part 6. We have a first step, a second amendment, where we add one little requirement, which is introducing global unique identifiers. We need that for various other parts. But then we will really start working on an edition 3 where we will integrate all these extensions to STL I mentioned earlier in my presentation. And we are currently in the process to select the topics that will go in the amendment in edition 3 of part 7.1, 2, 3, and 4. How does this process work? Maybe that's also one of interest to show. Some of you may be aware we have what we call a tissue process. Tissue process has been established at the very beginning when we started with 61850, when the first editions have been published. It's a process to deal with handling fixes in the standard that may affect product implementation. A standard of this size is never perfect. We are all humans and make mistakes, and you only realize that when you start implementing it. That's why we established the so-called tissue process. The tissue process over the year has then deviated a little bit in collecting as well new features. And we have now, on one side, moved back the tissue process to be really dealing just with interoperability issues and some editorial changes. Everything that is new features, for that, we now maintain a different database handled by the users group where we track all the future ideas that are collected. They can come out of a tissue, but they can come out as well from user feedback. We also have our user feedback activity. So we have now a database where we have a collection of all the ideas and features that we think we could do or we should do in the future to 61850. And we are now starting to plan the next edition. That's more or less this database that we are looking into. We have prioritized items there, so we will select from that a bunch of items that need to be going into the next edition. Of course, it's always as well integrating technical reports that have been published. And then we really try to have the process time-driven so that we have certain targets when the edition should be ready, and the issues that are not clarified by that time will be taken off the list to not delay the publication of what we already have. So that's more or less the process, how we are working now on planning the next editions of the standard. And I think with that, I'm at the end of my presentation. Any questions, comments, remarks? There's one question there.
Hi, Renaud Drouin from Hydro-Quebec. When you were talking about the system management, sorry, and the configuration update for across multiple devices, is there any mechanics planned in order to quickly know which configuration is on the different devices, or is it still based on a interrogation process?
I think I will forward the question to Thierry. He's the technical lead of that task force. I'm not involved in all the details there.
I'm not sure to understand well your question, if you can repeat it, but the system management first needed is to be able to upgrade the firmware on the STL file into the IDs in the interoperable way. And also, as you mentioned, to be aware of the version into the IDs, deployed into the IDs in terms of asset management.
So it's mainly on the firmware version that those mechanics are being worked on and not on the configuration version?
Both.
Both?
Both, yes.
Okay. But there's no mechanics standardized in terms of configuration version?
It's included too. You will be able to know the version of the firmware on the configuration file that you are into your IDs in real time by request, and to be able to upgrade it as you want in a tolerable way again.
Based on a configuration date?
Configuration date?
Well, we saw that across multiple devices, when it's on a date, either, well, it could be the same version on different dates, or either you force it manually and then it adds some complexity to know which actual versions. So in some cases, let's say a CRC check of the configuration can help to know which configuration version is on the devices?
Yeah, yes, exactly. This is a mechanism that you are including in the system management AD-7. And yes, correct.
Okay, thank you.
I think maybe the question is a little bit as well. I mean, in STL we have versions and revision information, but so far there's no clear way how to update this. And I think the question was a little bit, do we include some standardized procedures, how to use version and revision information?
Mechanism, but yes, it's correct that it's included into the system management mechanism, which allows you to give it.
Perfect. Thank you.
Okay, thank you. So you see, as a convener of the task force, sometimes you have to rely on your experts. I don't know all the details. I think there was a question over here.
Good morning, Tuan Vu from Powerlink Queensland and also Cardiff. So I just got a question. I saw you mentioned about the power quality. There's a plan for it. And I think, I don't know whether this question is directly related to 61850 or maybe an extension of it, but at the moment, from a utility point of view, there's a lot of data coming back, so PMU data, power quality data, as well as the digital fault recorders and SCADA data, and dealing with a huge volume of data trying to align them. And they're coming from different sources, different formats. So I'm just wondering if you can comment on the future or maybe the work in progress, maybe an extension of 61850 to somehow harmonize that data to help the utility to deal with the huge amount of data so we can actually collect them. Thank you.
I mean, when we talk today about power quality data, there is a technical report, 90-17, I think, that has been published a while ago that is describing models for power quality data. What I mentioned is that we had some discussions, we might need to revise that. I don't think it's really in the scope of 61 and 50 to start discussing how to deal with those data. So we provide the mechanisms that the data can be communicated to an application, but how to deal, how to filter that data, that's really, at least so far, I don't think that's in our scope. That it's more application-driven that need to decide that. Alex, you wanted to comment on that? Because you were...
No, I was agreeing with you, actually, because...
Okay. I saw you shaking the head. I was not sure if you disagree with me or with...
No, I was... What I want to say is that actually, for the different recorded data, pretty much ComTrade is the format that is being used as a de facto standard in the industry, and this is going to be revised to be based on XML as well. But the processing of the data is definitely outside of the scope of Working Group 10.
Yes.
So this is something that you can suggest maybe to SIGRE, to B5, to form a working group, because SIGRE is acting as an organization that creates reports to help address many of the applications of the 61850. Okay, and there are some activities looking into artificial intelligence applications for data analysis. So there is a lot of ongoing work in this area.